So welcome to our very first lecture of signal processing circuits. Today we're going to introduce the concept of signals and phasors. So in today's class, we're going to know what is a signal, what are the different types or categories of signals, basically classifications of signals. We're going to touch briefly on complex numbers, and then we're going to talk about impedance, sinusoidal functions, concept of phasors, and gain and phase shift if times allows. Okay, so let us start with what is a signal. Now, before I go there, can any of you tell me what is a signal? When you hear the word signal, what does that mean? The person in class or the people online? Generally, when you hear the word signal, what is the first thing that comes to your mind? Okay, something that is transmitted. Any other thing? What could that thing be that is transmitted? Could be what? Okay, you're thinking of it electronics. Okay, so you're thinking of it from a technical perspective, which is good. Generally, signal is information. When you're driving and the car in front of you signals right, you get the information that this person is about to slow down and turn right. It's an information. When you see the red light, you have to stop. It's an information that you have to stop. When you turn on the radio, your antenna picks up the radio signal, then you hear voices, which is information, right? So signal in general is information or data. That's in its abstract meaning. Now, this signal can be a function of independent variables, meaning it could be a function of time or space. So for the first example, the traffic light, how do you get the information? You know which color of the traffic light is lighting up. Is it red? Is it yellow? Is it green? So it's a space, right? It's an XY dimension. It's an image, basically. It's a picture that you're looking at it, and if it turns on red, that means stop, green, go, and so on, right? So it's a function of space, right? It's also a function of time. When time progresses, the value changes, right? So the signal could be a function of time or could be a function of space. For example, here I have the oil prices throughout the years. So this is a signal, and it's a function of time. Every year we have a different price, or every month we have a different price. So this is a function of time. An image is a function of space. A video is a function of time and space, right? So there are three types. It could be a single dimension signal, which means it has only one independent variable, which is time. An example of that would be temperature throughout the year, oil prices, audio signal, the voices. So how do you make sense of what I'm saying? It's because my tone changes as time progresses, right? So this is called a one-dimensional signal, which is a function of time. And then we have a two-dimensional signal, which is a function of space. For example, an image or a picture. And then we have a three-dimensional. And why is it two-dimensional? Because we have X and Y, right? So we have a two-dimensional plane. And then we have a three-dimensional signal, which is a function of space and time. So X, Y, and T. So we call this a three-dimensional signal. So this is one of the first methods, or one of the one ways to classify or differentiate signals. Is it a one-dimensional signal? Is it a two-dimensional signal? Or is it a three-dimensional signal?
So the previous example about the traffic light, is it second two-dimensional?
What do you think?
Because you told us it's a rise by time and space.
Which means
So it's a third.
three-dimensional signal, correct? Yes. Now, a signal can be prearranged variation in time, any detectable quantity or attribute. Now, how do I say it? This is a signal. An example of signal is speech. When I'm talking to you, this is a signal. It's information and it's progressing with time. Music, images, videos, and more specifically now, this is I'm talking generally. Let's now get more technical into what this module is about. Voltages. Voltage changes with time, AC voltage, right? Currents change with time, right? Impedances, right? Resistance, reactance, right? So these are all signals. We have pressure, temperature, and so on. Now, in this module, to be more specific, we're concerned with electrical signals, voltage, current, power, impedance, and so on. Okay? So up till this point, do we have a question? Online, are we clear?
Yes, everything's clear.
Okay, so now let's move on to the second classification of signals. Now that we've moved on to the types of signals, a signal can be classified based on how we can quantify it. Now, here I've mentioned that it's a variation of something that we can detect its quantity, something that is measurable, right? So, based on that, based on how we can measure the signal, we can classify it into two categories. A signal can either be an energy signal or a power signal. What does that mean? We know that the equation here, this is the energy equation. This is how you can measure energy. Energy of a signal f of t. Now we're speaking about one-dimensional signal, and from this point onwards, on this module, all the signals we'll deal with are one-dimensional in the independent variable of time. Voltage, current, resistance, these are all depending on time, right? So let's say we have a function f of t or a signal f of t. The energy of that signal is measured through this equation, the square of f of t from negative infinity to infinity. Okay? So, and we can generalize it to the magnitude or the absolute value of f of t squared. Now, if I look at this signal here, look at its shape. This is f of t, a function in time. Can you measure this signal by energy? So basically, do you remember what integration means? Generally, we said that if you have a curve, integration, let's say that this curve is f of t, it's a function f of t. The integration of f of t is the area under f of t. Do you remember that? So, if f of t looks like this, does f of t go to 0 when t goes to infinity for this particular case? Yes or no?
Miss, do you have your screen shared?
Yes. Are you unable to see it?
No.
For oh, can you view the screen now? Were you unable to see it the entire session?
I thought you were just explaining generally, that's why you turned it
I
off. But now we
understood.
can see it.
Without looking, perfect. Okay. Please let me know if there are any issues with the screen sharing at any point, okay?
Yeah, sure.
Okay. Back to our... Just a moment. Online, can you see the screen?
Yes, we can.
Okay. So if you look at this signal, you notice that it is starting from a very low value, and if you extend it, it's continuously decreasing, right? And if you extend it here, it's continuously decreasing, right? So, in order to be able to measure a signal by its energy, you need to know, because when you say its energy, you should give it an amount, X amount of joules, which is the unit of energy, right? So if a signal looks like this, or even looks like this, but gradually decreasing as it tends to infinity, that means that the area under it is measurable, right? Confined, which means that the energy will have a value. We call that an energy signal. Now, in contrast, what if we have a signal that looks something like this? and it's extending. What is the area under that signal? Infinite. So if I say the energy is infinite, is energy a true measure? No, because you cannot measure a signal that looks like this. What if the signal looked like this? Do you know what this is? Sinusoidal signal. So this is the area, this is the area, this is the area, this is the area, but it fluctuates infinitely. So what is the area under the curve?
It's equal. The you see, or
No, because you take the squared of it. So now the area is infinite or finite. So basically you're adding areas under the curve. Whether it's above or under, it's added. It's a positive value. So is the area under the curve finite or infinite? Infinite. So is energy a good measure of that signal? So in these cases, so if the signal satisfies this rule, as the function goes to infinity, as time goes to infinity, the value is going to 0, which means it's confined and the area under it is confined. You can measure it with the energy equation. Otherwise, if it's not confined, you can manage it with the power equation. And power is basically what? It's the average of energy over one cycle. So for this example, for the sinusoidal waveform, what you do basically is you take the same rule, the integral of f of t squared. However, instead of minus infinity to infinity, which we had here as our integration limit, we take it over one cycle from t over 2 to t over 2. So from here to here, minus t over 2 to t over 2. So you get the average. What is the average per cycle? Well, that's the power. So the average of energy per cycle divided by t. This gives you the power. So we call this a power signal. However, if the signal looks like this one over here, can we measure its power? It's not a repetitive, doesn't have a cycle, it goes to infinity, it cannot be measured by energy, it cannot be measured by power, so this is neither an energy nor a power signal. Clear? So this is a way of classifying signal. They can be an energy signal, they can be a power signal, or they can be none of the above. Okay? So this is the rule for it. Is it clear for us, for those who are joining online? Okay. So now we have two signals on display, signal A and signal B. Question is, what is the suitable measure for signal A and signal B? Let's start with A. Does it satisfy the condition that when t goes to infinity, f of t goes to 0, to 0? Are you sure? So this is the signal. The signal is basically goes up, stabilizes, and then drops down.
step.
Yeah.
So yeah, it satisfies the
So it's what type of signal? Energy or power?
energy.
Energy signal, because it satisfies the condition, so we call this energy signal. Can you measure the energy of that signal? So I'll write here the rule. Energy of a signal is equal to the integration between minus infinity to infinity of the signal squared with respect to time. Now, if you look at the signal, it has two sections. From -1 to 0, it has a value, which is 2. So from here to here, it's equal to 2, right? And then from 0 to infinity, it has a value which is 2e power minus t over 2, right? So based on that, I'm going to break the integration into two sections, into two segments. From -1 to 0, f of t is equal to 2, so 2 squared with respect to t. Plus from 0 to infinity, f of t is equal to 2e power minus t over 2 squared. Okay. From minus 1 to minus infinity, the value is 0. So there is no point of integrating. Clear? Now, what is the integration of 2 squared is 4. So let's write it 4. And 2 squared is 4, e minus t. Make sense? So we had 2e power minus t over 2 all squared, which is 2 squared e minus t over 2 squared. These cancel each other out, and this is a 4. Yes? So now we can integrate. The integration of 4 is, the integration of a constant is t, 4t. So it's 4t with integration limits between minus 1 and 0 plus the integration of e power minus t is minus 4 e power minus t, right? The integration of e power a t is equal to e power a t divided by a. And it's a negative et, right? It's e power minus, yeah, because it's a decaying exponential. Yeah? Okay. And we also have the same concept of integration limits from 0 to infinity. Okay? Do you remember definite integrals? So when you have an integration with limits, you apply the upper limit minus the lower limit in place of your variable. So in place of this t and in place of this t, I'm going to substitute with integration limits. So it becomes 4 times 0 minus 4 times negative 1. So that's the first integral, this one. Plus the second integral, minus 4 e power minus infinity, right? Minus 4 e power 0, correct? The first part, 4 times 0 is 0. Minus 4 times minus 1 is plus 4. So this is equal to 4 plus the second. E power minus infinity is? No. So it will become minus 4. E power minus infinity is equal to minus 4 divided by e power infinity, right? And division by infinity is equal to 0. When you take a very, so it is 0. So this is 0. And here e power 0 is 1. So minus minus 4 is plus 4. So it's 8 joules. The energy of signal A is 8 joules. Clear? Online, is it clear for you?
Yes, it's clear, Miss.
Okay, now let's move to signal B. I'll give you the answers. It's there, okay, and it's recorded. Let's move to signal B. Is that an energy or a power signal? It's a power signal because it's infinite, and it's what we call a periodic signal, which we'll see in a moment. So what we will do is we will take a single frame, the period, and then apply the rule of power. The power of a signal is equal to the limit of 1 over t, which is the average of the signal, integrated between minus t over 2 to t over 2 of f of t squared with respect to t. Correct? Now, if you look at the signal, what is the value of f of t? F of t is equal to what? When t is 0, when time is 0, f of t is 0. When t is 1, f of t was 1. When t is negative 1, f of t is negative 1. So within that time frame, let's make it clear. When t was 0, f of t was 0. When t was 1, f of t was 1. When t was negative 1, f of t was negative 1. So f of t is equal to t, right? Whatever the value of t is, it is the value of the function. It's a line with a slope of 1. So f of t is equal to t. So now I'm applying it here. So I'll say that the power is equal to the limit of 1 over t is the period. What is the period of the signal? It repeats every how many units? Every 2 units, right? Because it goes from negative 1 to 1, from 1 to 3, so every t units. So t is equal to 2. So 1 over 2, the integral between minus 1 to 1, which is 2 over 2, of t squared et, because f of t is equal to t. Make sense? Therefore, the power is equal to the limit of 1 over 2 of, what is the integral of t squared? T cubed over 3. Yes, you do that. Good that you remember. And the limits are from minus 1 to 1. So we substitute. It becomes 1 cubed over 3 minus negative 1 cubed over 3 times 1 over 2. So 1 cubed over 3 is 1 over 3. Minus 1 cubed is, okay, so minus minus becomes plus 1 over 3, which is equal 1 over 2 times 2 over 3. 2 and the 2 cancel each other out, and the power is equal to 1 over 3. What is the unit of power? Watts. So 1 over 3 watts. Clear? So now we can see a signal. You can decide, is it an energy signal, is it a power signal, or it's none of them. You can also measure the value of that signal. You can measure a signal. So that is one of, and you notice that it's always important to be able to measure signals, because you can calculate how much power it consumes, how much energy it needs. So when you become a design engineer, you can measure your signals and make choices based on these values. Is it all clear? So it's written up neatly here for you, and you can access this after the session. Now let's move to different methods of classification of signals, and I will go through these real quick because they are simple and intuitive. One way to classify signal is how they behave in terms of time and how they behave in terms of their amplitude. Are you familiar with the term amplitude? So let's have a quick look at these signals. Amplitude means the value of the signal in the y-axis. So x-axis always represents time. Y-axis represents value, amplitude, whether this value is voltage in volts or amperes or ohms, it's an amplitude. So let's look at signal A. If you look at signal A over here, you'll notice that signal A is continuous. There is no stopping of the signal, right? And if you notice, it's continuous in time and it's also continuous in amplitude. So we call this an analog continuous time signal. Okay? Now let's look at signal B. If you notice, signal B is also continuous in time. At any given point in time, signal B has a value, right? However, if you look at its amplitude, it's only alternating between two values, right? You can call it high-low or 0 and 1. Does that make sense, Yuna? So this type of signal that can only have a preset values that it can take is called a digital signal. So why is it digital? Because it's either a 0 or a 1. In contrast to the analog one, which can take any value. But it is also continuous in time because at any given point in time, if I take this point, I'll see this is the value. This point, this is the value. This point, it's a zero. At any given point in time, it has a value. So we call this a continuous time signal. Now, if you look at signal C, signal C is analog because it takes multiple values in terms of its amplitude in the y-axis. But if you look at the x-axis, time, it only exists at a pre-specified point in time. So we call this a discrete time signal because it only has specific values during specific points of time. And then we look at signal D, and you notice that it's both digital, which means it only has high and low values, and it's discrete because it has only values at specific points in time. So this gives us the first two ways of classification. In terms of amplitude, it could be either analog or digital. Analog means it can has any values. Digital means it will alternate between pre-specified values, 0 and 1, or high and low. And then in terms of time, you have a continuous time signal or a discrete time signal. So we have continuous versus discrete in time, and then we have analog versus digital in terms of amplitude. Then we have periodic versus aperiodic signal. So a periodic signal is a signal that repeats itself. It's repetitive, and it has a specific period, such as the signals we have here. It could be a sinusoidal signal, it could be a square, it could be a triangle, it could be a sawtooth, it could be anything as long as it's repetitive. We call this periodic. In contrast to aperiodic signals, so if I go to our previous example, this is periodic, this is aperiodic because it's not repetitive in time. Aperiodic, okay? Where are we? So this is periodic and aperiodic signals. And then we have energy and power signals, which we've already discussed. And finally, we have deterministic versus probabilistic. So what is deterministic versus probabilistic? Now, if you look at this signal, if I ask you to find f of t when t is equal to 120, will you be able to give me the value? Yes, right? Because we have a rule. F of t is equal to e power minus t over 2. As long as you have that rule or law, it can be easily calculated. How about this one? Can you give me the value of t when t is equal to 0.6? Yeah. Because with the calculation, so you have a rule. So we call this a deterministic signal, a signal that you can determine its value at any given point of time. There is a rule, there is a formula that dictates the value of that signal. In contrast to deterministic, we have stochastic or random. So the terms stochastic or random are the same thing. Or probabilistic. And an example of that is noise. We cannot define noise. You cannot have a rule that say that the noise at 5 p.m. in the radio will be this much. Otherwise, we would have solved a lot of problems. So we call this a probabilistic signal. Why? Because we can say it will probably be in this range. For example, temperature. I cannot say that tomorrow at 2 p.m. it will be exactly 40 degrees. But I can say, based on the information I know, it will be in this range. So it's probabilistic. Probably it will be this value. Similar to oil prices, gold prices. You cannot determine it. Probabilistic signal. Make sense? So this would be the different ways we can categorize or classify signals. How they behave in time, whether they're continuous or discrete. How they behave in terms of amplitude, whether they're analog or digital. Are they repetitive or not? Are they periodic or aperiodic? How can I measure them? Is it by energy or by power? And can I determine their value or it's completely random? So these are the classifications of signals. Now with that, let us move to special signals. Now, as we study this module onward, you will notice that we use specific signals, and we call this common signals. Okay, so I'm going to briefly explain to you common different types of signals, and we'll move on. The first type of signal is the unit step function. And as its name indicates, it's a unit, which means its amplitude is 1. It's a step, so it looks like a stair step. Before t equals 0, the value of u of t is 0. Once time becomes 0 or above, u of t becomes equal to 1. So this is the formula of that signal. We call that the unit step. Now the unit step can become a step. If you multiply it by 2 or by 3, the only difference becomes that the amplitude changes, but the value remains the same. And we usually refer to it with u of t. So whenever you are reading a problem and it says a function u of t, it's a unit step. Clear? The second type of signal is the unit impulse. The unit impulse, as the name indicates, it's a pulse. It appears in a very, very brief moment in time, almost 0. And the way we represent it is just by an arrow at t equals 0, just to indicate that it's very brief in time, almost 0 seconds. It's just a pulse and it stops. Usually, it actually is a rectangular signal, but this length is very small. Epsilon is extremely small, almost 0, and its height is epsilon. So when you multiply this length, which is from epsilon over 2 to negative epsilon over 2 and multiplied by height, what is the area here becomes? 1. Its area is exactly 1. And we call that the unit impulse. And we usually refer to it as delta, the delta signal. So delta of t is basically the signal over here. Okay? So you notice each signal will have like a specific variable that we use for it. So u is used for unit step, delta is used for the unit impulse. And then we have the exponential function, which we had in our previous example. An exponential function is in the form of e power a t. Now, an exponential has two types. It could either be an increasing or what we call a growing exponential when a is positive, or a decreasing exponential when a is negative. And this could remind you of the exponential growth of charge in a capacitor and discharge in a capacitor. Okay? Now, generally, when we're talking about an exponential growth, we always refer to the term tau, where tau is a time constant. And we'd say that at 5 tau, we assume that either the signal reached its maximum value or the signal reached its minimum value of 0. What is tau? How do we decide what is exactly tau? Tau is when the signal reaches 0.37% or 0.37 of its actual maximum value. So if it starts from a maximum of 1, once it reached 0.37, we call this tau. At 5 tau, we will say that it's effectively equal to 0. Realistically, it takes you to go to infinity to reach 0, but for mathematical purposes, for simplification, we say assume it's a 0 at 5 tau. Make sense? Is it clear so far? Because at 5 tau, it decays to almost 0.01 of its original value. So this is the exponential signal. Now, moving on, the final signal that I will discuss with you today is the sinusoid. And we will be dealing with a lot of sinusoidal signals through this module, so it's very important that you understand what it is, how it's described. This is the graphical representation of a sinusoidal signal. This is the visual representation of it. It looks like this. It has a positive half cycle. It has a negative half cycle. It could be a sine or a cosine. Okay? So, mathematically, this is the equation we use to refer to a sinusoidal signal. A sine omega t plus phi. A represents amplitude. This peak value, so from 0 to this peak value, it's A. So this is A. Omega is a sign of frequency. So what does that mean? We said that this is a periodic signal, right? So it repeats with a specific frequency. The length of the single period or the single cycle is called t. So we have a period and it's equal to t. And then we have a frequency which is equal to 1 over t hertz. T is in seconds, 1 over t in hertz. And then we have angular frequency, تردد الزاوية, which is, so this frequency is f 2 pi f, or 2 pi over t, which has the unit of radians per second. Clear? So if you know t, you can find f and omega. The angular frequency is called omega. So if you know t, the period, you can easily find f and omega. If you know f, you can easily find t and omega. If you know omega, so if you know any of these three values, t, f, or omega, you can find the other. So this omega over here represents this angular frequency. And finally, we have this theta, and we call this the phase shift. What does that mean, phase shift? Now, if you look at this signal, let's say that this is 0 and this is time. This is a sine signal, okay? The cosine signal is exactly identical in shape, but its peak value is not at 90 degrees. Its peak value is at 0 degrees. Cosine 0 is 1. So it is slightly shifted, right? So if you compare this peak to this peak, this distance is called a phase shift, which is, okay?
So if it's in the sine wave,
Theta is equal to 0, okay? If it's starting here and moving, theta is equal to, because this is 90 degrees, this is 180 degrees, this is 90. If it started here, then it's negative 90. Make sense? So this is the mathematical way you represent it, and this is the graphical or visual way you represent it. So we went through this. Now, when you look at a function, whether it's periodic, aperiodic, you can actually break it into either it's even or odd or a combination of even and odd. What is an even? And it's very important for you to understand now what is the difference between an even function and an odd function, and to be able to recognize them, because mathematically they will make your life so much easier when we go to the end of this module with Fourier series and transform. Okay? So now I just want you to understand the concept of an even and an odd signal. An even signal is a signal that is mirrored across the y-axis, meaning if you put the y-axis as a mirror, whatever is happening in the right side, it's reflected on the left side. Whether it's a square signal, this is even, or it's a triangular signal, it's even, or it's a cosine signal, it is even. Whatever is happening here is mirrored here. So if you treat this axis as a mirror, it's identical. F of t here is equal to f of negative t here. Make sense? Then we have what we call the odd signal. Now an odd signal is mirrored but with a diagonal, meaning if whatever happens, sorry, just a moment, whatever is happening here is reflected here, as if we have a mirror at the diagonal of the two axes. For example, this sawtooth signal or this signal, which is sine. F of t, the function here, f of t is equal to minus f of minus t. We call this an odd signal. Is it clear? Now every signal can be broken into a combination of odd and even signals. For example, the exponential. If this is your original signal, e to power of at, it can basically be equal to these two added to each other. This even signal and this odd signal. So if you notice, this part and this part, this is negative and this positive. So if you add them, they become 0. These are both positive, so when you add them, they become with a higher amplitude. Make sense? Up till this point, are we clear? Online, do you have a question? I'm assuming it's a no. Okay, now let's have a quick recap of complex numbers. Just to remind you, numbers we have natural numbers, which are 1, 2, 3, 4, full numbers without fractions. We have real numbers, which can be fractions, 1.2, 1.5, negative 6, negative 0.015, and so on. And then we have complex numbers, which are a combination of a real and an imaginary number. What is an imaginary number? An imaginary number is a number that has the imaginary complex unit j. What is j? J is the square root of negative 1. Now, if I ask you what is square root 9? 3. What is square root 4? What is square root negative 9? There are no two numbers that you can multiply them by each other and the result will be negative. It's impossible, right? Because if the number is positive, positive times positive is positive. If the number is negative, negative times negative is positive. So therefore, the concept of a number that can be multiplied by itself and give you a negative value is imaginary. It doesn't exist. So that's why we call this the complex unit or the imaginary number, J. Okay? Now, in math books, they usually use the letter I for imaginary, but because in electrical engineering I is reserved for current, we use the letter J for imaginary. Okay? So, a complex number, الأعداد المركبة, is a number that has a real number and an imaginary number. A real part and a real number multiplied by J, which we call the imaginary part. The way we represent them, just a quick reminder, there are 3 methods to represent complex numbers. This first form is called rectangular form, which is real plus j times imaginary, or the polar form. The polar form, or the exponential form. What is the relationship between rectangular and polar and exponential? We use Pythagorean theorem, نظرية Pythagoras, which is, let's say that this is the complex plane, where the real axis is the horizontal axis, and the imaginary axis is the vertical axis. X is the point where A and B intersect, which is here. This is X, right? Which is equal to a real A plus an imaginary B. Now, if I extend a line from the origin to point X, the length of this line is A, this A. And the angle that this line forms with the positive real axis is theta. Make sense? And using Pythagorean theorem, A is equal to square root A squared plus B squared. And theta is equal to tan inverse B over A. So this is if you know the rectangular form and you want to convert to the polar or the exponential form. And in contrast, let's say that you know A and theta and you want to find A and B. A, or the real component, is A cosine theta. And B, which is the imaginary component, is A magnitude sine theta. Make sense? Okay, so this is what we have. So this is the conversion from exponential to rectangular, from rectangular to exponential. And this formula here is called Euler's formula or Euler's identity. It's just the name that's given to this conversion. Up to this point, are we clear? Do you have any questions? Can you give me this number in its exponential format? So quick reminder, a is equal to the square root of a squared plus b squared. Theta is tan inverse b over a. Okay,
Formula was A or A minus B.
come again.
The x equals to A plus JB or with A and B.
Only a and b. J is the complex unit. You don't treat it. So this is your a, and this is with the negative sign your b. Okay. So this is equal to what? Square root minus 2 squared plus minus 3 squared, which is square root 4 plus 9, which is 3.6. And this is tan inverse minus 3 over minus 2, which is 56.31 degrees. So x is equal to 3.6 e power j theta, which is e power 56.31 degrees. So this is the number x in its exponential form, which is what we have here. No, it's written. We have it, okay? So up till this point, are we clear? Okay, so now we're running out of time. I don't want to go into a new part of the lecture, so we'll complete the remainder of this class next week. If you have any questions, let me know. Online, do we have a question? Okay, so I'll assume that's a no. We'll either let me just end this session here. And we will stop recording.